Okay, does this work? Yes. Indeed it does. So, welcome to the session on secure coding, taming bugs. I hope you will all enjoy it. So, what is this talk going to be going about? Well, the prime motivation for this talk has been that I've been auditing source code, finding bugs, exploiting bugs for the last 10 years. And after a while, it gets really annoying because you tend to see all those bug classes which are really similar to one another. So you tend to find SQL injection, SQL injection bugs, and people, penetration testers, attackers, and so on, can go to a website and just on their first attempt add one of those quote marks and they find a bug, an exploitable, remotely exploitable bug, which is pretty annoying because, well, that's just too easy. It shouldn't be like that. You shouldn't be able to find bugs that way. Not all bugs should be alike. There are quite a lot of really interesting bugs left that while doing a penetration test, you have very little time to find because you want to find the most severe ones. So you tend to overlook bugs in signal handling. I've just been talking before with Ilya about really nice hidden bugs in Unix system signal handling. And there are lots of unique bugs left, logic bugs left, that we don't find because all the bugs are too easy to find. Actually, there's some echo. Can someone turn down the test? Okay, I'm just going to continue, but there's some echo, so please fix that. So, well, I would like to see more interesting bugs because I do source code analysis a lot. It's very enjoying. I enjoy it very much to look for bugs, find bugs, exploit bugs, but it just sucks if they're all alike and too easy and all the same. There's no challenge there. So better code makes security more interesting. I think we will be able to move on. Also, the software quality will get much more interesting once we are past the basic bug classes. And, well, software security has been neglected for a long time. So we've been dealing with putting one box next to another box for a long time. And the problem with that is, for example, if you put up a firewall, you're basically doing that because you can't afford to patch all the bugs in time, even if you realize they are there. It's too expensive. You don't have the resources to fix all the problems at once. If you put up the firewall, it gets you some additional protection, some more time to fix before you can fix the bugs. But at the same time, it also contributes to deterioration of the security of the internal network because people then don't fix the bugs in the internal networks. And I think there is some ideal point where this all evens out, where the security gained by the firewall helps you get time to fix your problems. But at some point, if you add more complicated firewalls, application-level firewalls, intrusion prevention systems, and so on, some of them claiming to implement more than 100 protocols, that's just crazy because all or most of the bugs that we find these days are in protocol parsing code. And so if an intrusion prevention system or an application-level firewall implements more than 100 protocols, they are very likely to also have a security vulnerability in there. And then you get the worst case. You have the security vulnerabilities hidden in your internal network, which don't get patched because people feel secure, because the firewall and the application firewall and the IPS is protecting them. But at the same time, if it breaks down, if you find a security vulnerability in the firewall system, in the perimeter defense, then you get a worst case that's worse than if you hadn't had the firewall in the first place, because you're shifting the risk. So the risk gets consumed, the risk medication gets consumed in performance because people don't maintain their internal networks. So because of this, I think we need to move to actually improving the source code of the tools that we use, both the security tools as well as the applications. In this talk, I'm mostly going to focus on the security of applications that are confronted a lot with user input. So I'm going to talk about how we have dealt with daemons, network servers, and web applications that deal with a lot of protocol parsing, parsing of user input, and so on. And the primary bug classes that are found the most. And what has happened so far in our approach to dealing with security vulnerabilities, we've had two primary approaches. One of them has been education, so just saying, well, just escape your input if you use it there, or check for the buffer length, check for the buffer boundaries if you do this, and going further, introducing new APIs like strlcopy or strlcat, which are supposedly more easy to use than their counterparts like string copy and string encopy and string encat and so on, which I think is a good thing. Having more intuitive APIs can help a lot. But then the education goes along the lines, oh, never use string copy, never use string cat, just use string encopy, just use string encat. I will talk about the problems of those two approaches. Then there's a third approach, which is abstraction of the problems that we are dealing with, which I also call sometimes the accidental approach. So yeah, we are actually trying to solve a non-security problem, and while doing this, we actually improve our security. This has happened with automatic memory management, with object relational mappers, and all kinds of abstractions. These things have seldom been actually used with the intention to improve security. In the example of buffer overflows, which I'm just going to use as an introduction, the real cause of the problem is that program flow ignores memory boundaries, so that you're either going to write beyond memory or read beyond the memory of the allocated buffer, or access using an indices, some memory outside of the area that you have allocated and actually want to access. And this can be triggered in a variety of ways. One of them is by using array indices, which basically means x and the square brackets I, and I is a value which is outside of the boundary that you actually have allocated. So it's a too big value or too small value of I. Then there's the string copy, string cat, and sprintf functions, which create, which you can basically still create problems even if you use the more secure counterparts, which just copy beyond the boundaries, and it's pointer arithmetics, where you add pointers or multiply pointers, and you get to regions outside of the memory that you really wanted to access. And from the education perspective, the way we've dealt with that so far has been saying, oh, use a different API, use string encopy, use string lcopy, and we didn't really have education mantras for saying, well, how do you do an iteration over a string array? So we can only deal with the most basic things using those mantras. The tricky problems, we won't be able to deal with that. Even good programmers get problems in their code with pointer arithmetics and with indices into the code, into the buffers. Then we've been dealing with various ways to protect against a perceived problem with buffer overflows. So we might misinterpret the problem, not of there existing a code flow that actually might access memory outside of the boundaries, but that the code is able to do so. That's what happens when we try, for example, stack canaries, which basically means we add some secret value after the memory, after the buffer, and we try to protect there by checking if this magic value is intact after the fact, after the write. Then there's another way we might interpret this problem by saying, oh, the problem is that the attacker can inject their own code and then execute it. So we use write XOR execute, which means you can either execute a memory region or you can write to it. And so we protect against that. We could also say the problem is that the attacker can execute any code if he knows where it is. We just hide where it is. But all of those protections, they don't really get to the real point. These defenses make exploitation harder, but they don't deal with the real problem that the code just tries to access the memory outside of this boundary. So reducing exploitability is just treating the symptoms. So now we get where we really want to be. We need to improve the code quality if we want to get beyond just treating the symptoms. We need to be able to write code that is more secure. We can't really measure if code is secure. We can only prove there are security vulnerabilities in it. We cannot prove they are not there, but still there are some design considerations, some design strategies we can take to make the code more secure, and they seem to work, even though we don't really know how to measure them. For example, using abstraction of the whole string handling, the very secure FTP daemon by Chris Evans has been able to be one of the coolest FTP daemons out there. And it, as far as I know, it only had one security vulnerability found by the author in about 2001, which was a signal race condition. And it's used on big sites like Red Hat FTP server, OpenBSD FTP server, SUSE FTP server, and so on. All the big FTP servers use it. And basically, what it does is two things. It abstracts, it has a nice design by taking the security critical portions and putting them into jails like change root, taking away the privileges and the capabilities. It runs the secure socket layer handling code with all the buggy ASM1 problems there. It runs it in its own change root with its own user ID. So there's nice abstraction in the design on the one hand, but on the other side, there never has been a breach like a buffer overflow or anything in the code that would have necessitated this kind of design. So even though the design is really nice with all this least privilege design and jailing the components into different user IDs using different processes to split the privileges apart, this hasn't been necessary because VS-FTP daemon implements its own string handling library, which is opaque to the user, and so you cannot really fuck up the code at that point. So only the library code, only the implementation where you think about what you're doing could embarrass itself with a string buffer overflow. Well, there are more problems similar to that we could try to deal with in the regard similar to buffer overflows, data access problems. We could abstract the string handling, which means we just store how long the string is and don't have that implicitly in the code. We could abstract iteration in a way so we don't accidentally, if we iterate over a buffer, go outside the memory area. We could abstract memory allocation, deallocation, so we don't have to deal with free ourselves, and count the amount of passed arguments for var args, which is what format strings are doing, so we don't accidentally take more from the stack than we need to. We could wrap index access into buffers with bounds checking, so we have a function which does get, and we use that to access the memory, and it does automatic bounds checking for us. And we could use high-level integer types or any other abstraction where we don't use the integer types anymore anywhere else in the code to avoid signedness misinterpretation and automatic conversion and so on. But we are going to miss some of those problems. That's going to get really difficult. I will say, yeah, I'll come back to this. The thing is, all those bugs have in common, and all the bugs like cross-site scripting bugs, SQL injection bugs, and all the common bug classes right now have in common, it's not something in the design, it's not something you mess up once and you can fix once, but it's something that is spread out all over your code so that the places where you can make buggy code statements grows with the amount of code you write. You don't get it once right, once and only once right. So we need different approaches that allow us to write code in a way that we have to write, we can get it once and only once right. We can get it right once and only once. So what's happening there is if you give a lot of different programmers the same tools and the same task to implement using those tools, they will make the same mistakes. So if we look at, for example, ASN1, which I've mentioned before, which is used in lots and lots and lots of security critical protocols, for example, SNMP, SSL, the ASN1 compiler, of course, Kerberos, then what's it called? Well, it's used in the common internet file system, it's used in the phone system, in S7, it's used for ground air communication. These are the non-public implementations. It's used in the internet key exchange, VPN implementations, and so on. It's used in Secure Shell. You have ASN implementations everywhere. ASN1 basically is a protocol. It's a notation for encapsulating how you transfer data. And all the ASN1 parsers so far that I could find have had some kind of security critical issue. So this goes for 2 pages. And all of them are written in C, all those that are listed. And they all make very similar have very similar problems. So there's the Protos project at the University of Oulu, I think, which writes protocol testing frameworks. And their protocol testers find very similar bugs in all those implementations. Some of them really almost equivalent, even though they are completely independent implementations, many of them. So the GNU TLS project, for example, was trying to re-implement OpenSSL because of security considerations, among other things. And they made quite similar issues and problems at some points as the project they were trying to imitate. So if you give someone the programming language C and give them the task to implement an ASN1 parser, they will make similar mistakes. And that's why it's so easy to find a bug. You look in a web application and you know people will fuck up when they write a SQL statement. So, and to deal with that, even if you're a good programmer and you have a deal of excellent programmers and you're working on a project, you don't really want to deal with a single bug. If you find a bug, what you really want to do is, of course, you want to fix it. But then what you want to do next is you want to think about how can you put yourself on rails in a way that you yourself will not be able, even if drunk and out of your mind, you will not by accident make the same mistakes again. So this is the kind of things the really good programmers do. This is why VS FTP daemon is quite secure. This is why I think Daniel Bernstein's QMail and so on, C code is quite secure, despite it being very hard to read. Some of you might know about that. And all the good code I've seen so far does not depend on good programmers not making mistakes, but good programmers not letting themselves make mistakes by putting themselves on rails. So that's an illustration of that. What you really want to do is you want to change the landscape of the programming environment that you're using. You want to put up different abstractions that change the terrain. So if you let 1,000 people play the game of Marble Madness, you will get some statistic distribution of where people have problems, where their marble will fall off the terrain. And if you change the terrain, you will have different places where people have problems. And by changing your programming environment, by changing the library abstractions that you use, you can mitigate a lot of problems. So abstraction is the key. VSFDB daemon is a really nice piece of code to look at for how you can create those abstractions in the C programming language. Basically, it does some kind of object-oriented programming in C, where it abstracts all the string handling away. I put up just the struct that it's using to represent strings. And then there's lots of special case routines like netfd read, which just reads from a network socket. Then there's string change mod, like normal system calls like lstat, syslog, open, and so on. The problem with that is you need to write such a routine for every single place where you would normally pass a string, every function where you would normally pass a string, and now want to pass your own special string, your own string representation. So that hasn't caught on very much. In the design documents of VSFDB daemon, Chris is, I think that hasn't been updated in a while, to be honest, but he is wondering why that hasn't caught on. This style of defensive programming, of not letting yourself make mistakes, why that hasn't caught on very much in the C world. And personally, I think it's too much special casing, it's too hard to use. You just need to write your own routines for every place where you would, for every library, every function where you would normally pass a normal string buffer. And on the other hand, I think it has caught on in some way because many high-level languages provide a more general abstraction where you don't need to write special casing code and you get automatic bounds checking for free with any string you use in that language. And many other problems of memory management have been dealt there at a single point, once and only once. So if the language implementation is correct, you won't have buffer overflow problems in the strings there. And to be more specific, the problems that can be dealt with in fairly easily and fairly generally in high-level languages are stack overflows, heap overflows, off by one, double free, missing memory initialization. So basically a variable where you don't put any data in before using it, format strings, unchecked indices in array access, and integer overflows. Just an aside, because I recently read an article by FX about, it's called, I think, software security, software reliability. You ought to notice that we are classifying those bugs by their exploitability and how to exploit them, not by what the actual fault is. So an off by one is not that different from a software fault perspective from a stack or heap overflow. And we might misclassify and buffer overflow as denial of service because we think it's not exploitable. So I think this is an area where we can also learn a lot, just classical software reliability management, where we prioritize for problems that have security problems. So those bug classes can be dealt with by abstracting the memory management, the data types, the data access, the way we reference it, getting rid of pointer arithmetics, finding different abstractions that are more suited to what we are trying to do. And if we look at this nice graph from Felix's paper in the Communications of the ACM magazine from just recently, we can see that this kind of change in moving to a higher level language, mostly by accident and for other reasons, but still has had some impact. So if you look at the green bar, you see the data reference failures, which is just the software quality name for all these buffer overflows, integer overflows, and so on. So data reference failures have been on the decline relatively to the other bug classes. We're seeing a lot of input-output errors these days, so that's what I'm trying to. I will focus on in the last part of this talk, how to deal with the current problems we have with input-output errors in a similar way to how we have dealt with data reference failures using abstraction and high-level languages. We have seen a fairly constant amount of logic flaws, which I think are, at least some of them, are the really interesting bugs. And, well, we have seen some, basically the only class where we really made a difference so far is data reference failures. And this is all the benefit of the high-level languages. So that has happened by accident. And what I'm trying to argue for is we can replicate that. By studying why we face less data reference failures right now and what has worked, what hasn't worked, what works for some people but just doesn't scale to a bigger team of people, I think we can deal more effectively with the other vulnerability classes too. So just to sum it up, if you use those abstractions, you have, it gets much harder to shoot yourself in the foot. So you should use abstractions, and you should use abstractions that put into the code what you are really trying to do, because that makes it easier to read, easier to audit, and even for programs using static analysis, if there's more information in the code, it will be a lot easier to find the problems later on. So what are the downsides of abstracting? Is it really, doesn't things get slow if you use high-level languages? Doesn't it just move the problem? You do bounce checking on every access and so on. And there has been some interesting research in the direction, and the results are, it actually might get faster. For example, if you got a modern graphics processing unit with its own processor on it, you might have some C code which is doing some things using with vectors, but the C doesn't have a representation for a vector type. So you have the problem that you will do it using loops, and it's very hidden, all the vector handling, and it's very hard or almost impossible to just analyze the C code and find out that you're actually trying to deal with vectors, and then automatically pass that to the graphics processing unit processor. So it will not be easy to optimize that automatically. On the other hand, the Fortran language, which is older than the C language, has a vector type, and it's very easy there. It's just unbounded vectors and not just the size of 4 bytes like the graphics processing unit needs it. So you can automatically optimize that in the compiler. Then you have about 150 parallel instructions on a P4 processor. Right now, manually optimizing that is a lot harder than just putting a lot of information on what you're trying to do into the code and letting the computer figure it out. And other reasons why we have this perception that abstraction makes things slower instead of faster, which I think might happen in the future, is that some high-level programming languages like Java have just chosen the wrong abstractions, basically taking a low-level data type like the string array and trying to put high-level semantics on it with bounce checking on every access. There are better abstractions you can use for many of the data types that Java uses, which are more high-level and provide different semantics. And just to show that this really works, the IronPython.NET implementation is actually faster in many tests than the C implementation of the same thing. And they're even trying to re-implement Python in Python as a high-level language, and even that probably will get faster. So it might, for a short while, abstraction might have downsides in the speed area, but in the end, it will make it easier if you put a lot of abstraction into your code for static analysis and for optimization. So just that as an aside. Well, so personally, when I do code auditing, I really love it when I can work with clients that don't just want the bugs pointed out, but they also want feedback. How can they change the code to make it easier to audit, to easier find bugs? And so I would, if you have a software development process that you're working on, I would define it there that using bad APIs, for example, for database access, is a bug in itself. Because if you use an API that makes it easy to make SQL injection mistakes, it will be very hard to find and fix those later on in your code. And the same goes for using broken abstractions in any security critical area. So if you identify that something is bug prone, deprecate it, use something different, use a different abstraction. Okay, and then use code audits and maybe static analysis. So if you've defined that some abstraction is broken, you don't need to look for specific cases of using that abstraction where there is a security critical problem, but you can just say you've got a problem already by using it. So sometimes for execute query statements for SQL injection, you could just use grep to look for these. Use prepare statements instead. Okay. So for the rest of the talk, I will go into some approaches that I thought of how to deal with other bug classes other than the data reference failures. And some of those are the SQL injection, XPath injection, LDAP injection, all those injection problems, which are quite related to the cross-site scripting problems, meaning you put the wrong data in the wrong place. You mix different data types on a semantic level, path traversal, and then problems which are part of the programming language itself, excuse me, including insufficient hemming distance, programming language magic, and insufficient expressiveness. Okay, so here's an example of insufficient expressiveness. If your programming language does not support iteration over arbitrary lists, you might do something like use an integer counter and then go over count with that integer counter using a for loop, and then accessing using array indices, accessing each element of that list. So I have here two different bugs. I'm going one field too far in my iteration, and because I use lesser than argc, and I don't reference. I always reference the second element of the list, because I don't use the X that I just defined for that in the actual access. So I have two different problems. Then I can do. I have an off by one, and I reference the wrong element. And this is just because the programming language doesn't support arbitrary iteration. If I had a programming language that would support arbitrary iteration, I could just do, for every element in argv, do something with that element. It's very hard to create a problem using that kind of setup. So a high-level construct just puts in more, says more about what I actually want to do, because the compiler doesn't really know that I don't want to count integers, but I just used it as a helper. So I should tell the programming language what I really want to do. Another example would be, I would want to list all the files in a directory. And in the PHP programming language, this creates a problem because, well, as you can see here, they had to introduce a third, like you have equal, 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 we all know those, but they had to introduce equal, 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 and not equal, equal. So just another operator, because their compare operator automatically converts types. So if you compare against false, normally this might iterate over all the files in a directory unless there exists a file named false. So this wouldn't really work, and also it's really ugly. It would be much nicer to use an iterator again there and say what you really want to do, not do some read dir and file equals this and then is it false, but you just want to go over all the files. So you just tell your programming language for everything in that directory, give me an X that I can print. Then another problem in programming languages is the hemming distance between various statements. Hemming distance comes from coding theory, which just means if two code words are too similar, the Hamming distance defines how far apart two code words are. If they are too close, you get a problem because in this case, for example, if you lose one equal sign, you actually assign a value to x instead of just comparing. That's a really nice way of introducing a backdoor somewhere. I think something like this was tried to be introduced in the Linux kernel a while back. I don't know if I think it was with an equal sign, but these kind of similar statements, they just, if you just skim over the code, you don't even notice. Of course, this can be found again using static analysis tools, but not by checking whether this is a security problem or not, but just saying this is evil by itself. If I find something like this, even if it works, I should just refactor my code so this is a problem, even if it's not a security problem, because it might be a problem that makes my code unauditable and I will have more problems. Then there's another thing which happens in many programming languages, which is automatic string concatenation, which happens when when you put two strings besides each other, even on different lines, they automatically get concatenated, and so the second array down there just contains 3 elements instead of 4, because a comma went missing, and you don't even see it. Like if I skim over the code, I might not notice, and this might yield to illicit data references again. So that's a real problem. You don't really want to have automatic string concatenation without an explicit operator in your source code, in your programming language. So if you find something like this, personally, I would also flag it as a problem and try to refactor my code so I use explicit concatenation operators. Because then it's really easy. I just go over the code using my automated program, and whenever something like this happens, I can just fix it, get rid of it. I don't even need to think about it, whether it's a security problem or not. I just fix it. Then there's another problem, which is programming language magic. I won't spend too much time with that. PHP is full of that. For example, it's automatic variable assignment. You just pass something to a PHP script, and it automatically defines a variable with those contents for you. So if you forget to define a variable and you just assume it's undefined before you use it, you get, security problems very often. Then there's fopen, include, and so on in PHP, which accept also URLs. And for include, it even downloads remote code and then executes it. And if you disable that feature, at least last time I checked, there is no library or anything with which you can do your HTTP requests. So the suggestion I got from PHP programmers back then was to just open a socket and send get/HTTP and so on. So either you take the full package where you wide open the security vulnerabilities, or you write your own HTTP client implementation. Then undefined variables that automatically get defined as empty, because then you don't notice you're using an undefined variable, which in combination with automatic variable assignment can get really bad. Then automatic type conversion of variables. For example, in this case, $ID equals my string is true, and if ID is a string that contains my string, which is obvious, or on the other hand, if ID is an integer with value 0, then my string gets converted to an integer of value 0. So that's true too. That's not so obvious. So my string would get converted to integer because the first argument ID is an integer too. That's absolutely not obvious to me. Then there are the injection problems. So those problems can be fixed in the programming language. Some programming languages are better choices from these perspectives of not tricking you, hiding things from you with weird syntax than others. None of them are perfect. now we are getting to the injection problems. There are the SQL, LDAP, XPath injection, and also cross-site scripting. They are all caused by injecting data of one type, so just plain text, data coming from the user, into data of another type, which might be SQL, which might be HTML, LDAP, and so on, without converting it. This is not a type conversion in the programming language sense, that you have types in the programming language where you don't convert, or you get auto-converted or things like that, but it's just you have a string, and the string has some meaning to it. It's not just data. You can treat it just as data then, but then you shouldn't execute it. You wouldn't dump some random data you got from your random device on your command shell. It wouldn't make sense. So the problem is, if the data comes from the user and you put it into an SQL query, then weird things happen if the user has control over the data and you forget to explicitly convert. So by looking at this from where we were at the beginning, we have to do this every time we take data from somewhere the user gave it to us and plug it into some other data where it has meaning, and it's easy to forget about that. So the problem is, or the thing we are trying to do, is we have to find a way that avoids that we cannot forget. So we want to be certain that we cannot forget to convert. So for example, for HTML, which is what I'm going to look at first, we always have to escape the code before we insert it into a website, into an HTML template, or if we put it into an URL that we are linking to from our HTML, we have to make sure we escape it so it can fit into the URL. And the same is true for SQL. We have to escape the code so we can put it in there. So what I'm proposing is to use the type system of the programming language to enforce that. So instead of just saying we have just string, and we send a string to the SQL server, and we put a string into the HTML template, and we take the HTML template, which is just yet another string, which we then print out to the browser. We actually use strings to keep track, to allow the programming language to keep track what data is contained in the strings. So we have HTML strings as an actual type and SQL strings as an actual type. And we have two choices. Either we just give a type error if we try to put a plain text string which hasn't been converted into an HTML template, or we could do automatic conversion, which we prefer is a matter of choice and also on where you are going to use it. So in the demo that I'm going to show now, all the strings get auto-converted to HTML string before being output. Also, I had an extension in there that you could define in the database model. So if you put user data into the database, that certain things from the database are stored in HTML already, and they don't get escaped again. So I will try to show that, but the resolution is a bit weird. Okay. I'll just add a post. I have a blogging demo application for this. Just put some code in there. Here we are, which contains HTML here. Then I will post a comment. Okay, so on the comment view page, I have a cross-site scripting problem now. And if I look at the template, if I look at the template, for comment in comment list, it gives out the comment person name, the person name of the person who gave the comment, and it just puts it in there. And so of course we get a cross-site scripting problem. Now if I change this to use my modified code base of this framework, it gets automatically escaped. And this is just happening because I changed the template language to keep track of whether a string has already been escaped or not. I will give out this code after this presentation, this demo code for this. It's quite an easy implementation, so I just implement different string types. I do something similar for, I've done something similar, but I've taken a different approach for the SQL injection. So basically, this framework, in this way, it breaks a little bit of compatibility, but it should be fairly safe against cross-site scripting, because you just have to explicitly say when you want to unescape something. So I do this in the code here. I've implemented similar things in different frameworks. I've worked with people who did this in Java. So basically, whenever I want to unescape, when I want something to be displayed as HTML, I just add a filter which unescapes it, which just adds information that internally it converts the string to the type HTML string. Good, I think I'm a little bit short in time already. So I will need to hurry up a little bit. Good. Using the other approach of using the database model, it's really easy to verify that nothing happens that breaks the model. It gets really easy to statically analyze it, because basically all you need to do is analyze your templates, which is kind of weird, but it works. Also, there's a different approach for protecting links, which also works. So I think this is fairly safe against mistakes. Then there's SQL injection, which you all know. So in PHP it looks like this. You just concatenate the data in without caring. Same thing happens in Java if you don't use prepare statements. In PHP you can fix this using escaping, or in PHP 5 you can fix it using also something like prepare statements, which is new in PHP 5. Then in Java you can fix it using prepare statements. And here, by just putting in the data and getting the auto escaping there, it gets really easy to audit this, because now if you say the prepare statement template, so the part in the first line where you define select and so on, has to be static. It's a constant. It gets really easy to statically analyze this. You just say, I never want to have any non-constant templates for my prepared statements, and then you are probably safe. Then there's some. Then I just wanted to show the approach that most Java forks have been taking for a while with abstractions. So there are data access objects, which just means you write lots and lots and lots of glue code, which is accessors where you change all your data, and they actually start set off the statements that modify the database. This doesn't help at all with SQL injection. It just requires you to write lots and lots of code. So many of the design patterns, it's not about just doing abstraction for abstraction's sake. I mean, data access objects have other advantages and they're quite nice, but they really require a lot of code. So it's not about making any kind of abstraction. It's about choosing the right abstraction that really solves your problem. And for SQL injection, one nice approach besides the typed string approach, which is quite similar but a little bit different to the cross-site scripting example I've showed, is to hide the SQL for programmers. If you don't write SQL, you will not be able to make a mistake. So instead of writing SQL directly, you use an abstraction language within your own programming language. So for example, a query might look like this, which is Python code in this case. And you won't be able to create a SQL injection problem with that. So I'm just going to make this real quick. I mean, it's not going to look impressive, and it's very simple techniques, but applying these throughout the code might really help you get rid of the whole bug class instead of just single bugs. So what I'm going to do here is just add an SQL injection here, and then show how by changing the code a little bit and using a different abstraction, you will get rid of the problem. So we have a classical SQL injection here, just by taking the slug part of the URL and putting a little bit of putting a quote and then a little bit of SQL in there, union select, and we have the hash of the password. So to fix that, what I'm going to do is go into the code and switch from manual SQL queries to automatic SQL queries. So this is basically the backend code. That's the model. So basically, I'm going to replace all this junk here with that. Yeah. So now it says post-matching query does not exist because, of course, it now interprets it as string, as it should. I'm just going to go back there and verify that the functionality is still working. So, yeah, still working. So just a simple change. So I do object, post objects get instead of constructing my query manually. And with the condition, that's the row slug equals slug, the column slug equals slug, the variable slug. I've solved the problem. If I do that everywhere and then just blacklist and do some grep regularly that no other SQL access is used besides this, I'm safe again from SQL injections. So again, I just get rid of the abstraction that is causing the problems for me and replace it with something else. So that makes regression testing really easy. Check that the template is constant if you choose to use the prepare statement abstraction. And none of this works with generated SQL. If you need it for performance, just do it where you need it. Then it's still easy to audit because you shouldn't need it very often. It should be just in one or two places. You wouldn't need generated SQL too often. Okay, I think this is the last thing I will be discussing, the last defense technique I will be discussing today. This is really one of the very, very, very simple ones. The problem is it's path traversal or file traversal, where you open some path from outside the directory where it is supposed, using // and things like that. And so you just concatenate your variable to whatever path, and people escape from there. Often people tend to do things like looking for // there, for this // part there, but that's not the best solution. For example, Microsoft had a problem in IIS with Unicode because they were just looking for certain portions. They didn't choose abstractions. The different parts of IIS and the operating system dealt differently with Unicode, or didn't deal with it for that case, which even led to a remote coded execution problem. So that's not the nicest abstraction to just check for // and say that's evil. It's also // it might be different on different operating systems in some cases. So there's a much nicer way. I will there's at least 10 minutes left for questions. So basically what I'm saying is, what you really want to do is you want to normalize paths before comparing them, which means you convert the path to a representation that is unique, that is unique to the whole operating system. So you have a lot of different representation for paths. You have relative paths, which don't start with a / then you have, and are relative to the current working directory. Then you have absolute paths, which are starting with a /, but they still might contain // So you might access the same file using lots of different paths. And then there's the normalized form, which starts with a / and doesn't contain any // parts in it. So it's one, you can convert any path to a normalized form which is unique and which you can compare against. So the nice thing about this is, if you convert to a normalized path, you can then so here's the buggy demo. So here I can access a file that's outside of the path that I'm allowed to access. And in the other demo, I'm going to show this code in a second. This is not allowed. So how do I do it? I think this is quite a nice abstraction, even though it's very simple. Basically, I wrote a routine which is open within path, which first makes an absolute, which first joins two paths independently from the operating system. So it joins the data path, which I've defined up there as var demo web data. It joins it with the file path that I've just received from the user, and then I just check if the path is in data path. It works. Also another way, I think it would be nicer here. If it just starts with it. If the path starts with the data path portion, so it's not outside. So otherwise I throw an exception and everything is fine. So the nice thing about this again is I've clearly specified in the source code what I want to do. It's even nicer than doing this inline, because I really specified what should happen and what should not happen, and then I can look at all the other calls to the open statement, and I shouldn't have any. I mean, I shouldn't have any other open statements that are seeded with user input. So that works very nicely. Again, I can do very nice both auditing and static analysis to verify, or just regression testing to verify that my code conforms to a certain standard. So, oh, and one last demo is cross-site request forgeries. That's the problem where you, for example, where you go to some other website and it contains an image link back to your site with, like, it happened with the website Dig, I think. It happened with Places, which some of you might know. It's just some website where you can pinpoint where on the globe you are. And there you just, if you added a web image link on your weblog, for example, you could add a link to /add-friend /username. And if the person was logged in, this image link would automatically add you to their friends list. You could do the same with a link to change password. So that's the reason why GET requests should never change any state in the web application. That's the reason why we actually have GET and POST requests. The difference is not that you see it up there in the address bar in the case of GET and you don't in the case of POST. But the real reason we have them both is that GET requests shouldn't alter the state and POST requests should. So the real way to do it is not to change state on GET requests and then find a way to protect POST requests, because you can still use in JavaScript and iframes. You can really easily for example, if someone is logged in the admin interface and then visits your website, you can add yourself a new user and give it admin privileges using cross-site request forgeries. So I think there's another talk at Black Hat about it if you're curious about CSRF. So I'll just provide a protection demo, which again doesn't require you to change every single form that you're using to protect against cross-site request forgeries, but allows you to just deal with it once, which is all we're trying to do in this whole talk. So for last thing before I take 5 minutes of questions, I'll just give a short demonstration of CSRF protection. So basically, I have this here. I would change my password here. It works with anything else. Normally, you have enter original password field, so it wouldn't work there because the original password kind of works as a session protection, as a session key, but there are many interesting problems that work with CSRF, so I'm going to demonstrate the CSRF now by going to a different website, which is localhost csrf demo.html. And basically what CSRF demo did, I'm going to show this. It's just some JavaScript code to redirect to the post action on my server with both times the same password set, and using this submit, I just set the password for a logged in user on a different site than the one he just visited. And using an iframe, I can make it so that the user doesn't notice. The way to protect is to add a form field with a session key somewhere in there, other than the cookie, because the cookie always gets sent, even if you come from a link from a different website. So the way to do it is, in the case of this framework, is to add another middleware which changes every form that is given to the user and adds a session key there. So if I try this again now, I just loaded this middleware. So if I'm going to try that now, I get cross-site request forgery detected, request aborted. So if I try to just to demonstrate what has happened using this middleware, a middleware token has been added automatically to the form. And using this token here, we are safe. Again, this happens automatically. You don't have to change anything anywhere else in your code. So again, we have protection that scales with your code fairly well. Okay. Well, there's more. There's the layered design I mentioned before. Split up the code to run with least privilege. Protocol parsing code is very bug prone, so put your protocol parsing code into a jail with its own user ID and so on. VSFTP does this very nicely. It jails all the secure socket layer code from all the other code and uses inter-process communication in there. Write high-level code that's very easy to audit, use abstractions that really say what you want to do. And first of all, get the basics right. Don't repeat yourself in bug-prone code parts. So I think that's almost more important than the layered design, which is a worst-case protection. But if we get those basics right, we're a lot further. We can really deal with those bug classes. So finally, questions? Perfect. Thank you.